All right. So tonight we are talking about torque, rhymes with fork or spork or cork if you've just popped a bottle of wine for a light afternoon physics class. Not recommended. You know what they say, never drink and derive. Ouch. Anyways, all right. So let's start with an example here that I was thinking we might try. Yep. So bad, so bad. All right, now look at this. We're actually looking. Oh, nice. Yeah, like one of those pomegranate bottles. That's, yeah, very good. I like how we're getting some advanced physics humor here. That's like worth an A, right? Okay. So, oh, you know what? Before I forget, let me mention a couple of things. There's a group activity at the end of class today. So that's at 30 minutes before the end, which is what, 6:15, I think. So at 6:15, there's a group activity. And then I'm going to send an email about class next week. So, in short, no class on Monday. I might send you some videos you could watch, but probably class next Wednesday. All right. And we'll do an I'll send you an email about this later, just so you can understand. That way we're not eating up the clock for class time. But so basically the thing that you need to know is no class Monday. All right. So you don't have this. You can work on practice tests or chapter 10 homework or all the different things that we've been working on. And like I said, I'll try to send you some videos there. All right. So now we're up to this problem here. And now I'm going to loosen this screw a little bit. And I want you to watch what happens to this thing. So I'm trying. Okay. So it starts to fall down, right? And if I keep my finger locked here, you can see it starts to fall down more and more and more. So instead of being perfectly level, now it's instead of being perfectly level like this, it's starting to droop. So if I tighten this back up, you can see it starts to level out again. And so I would like to point out there's a natural tendency of this rod to rotate downwards. That means you could think of this experiment as a pivot right here. There's a pivot point, and if I loosen this screw too much, this will start to rotate down. Similarly, you could think of it a lot like this scenario here. Now, I'm just going to bring this close to the monitor for a second. Okay, so remember, this is our old friend, the spinning rod with two pieces of brass on it. Now, if I bring this close, remember, there's a screw right there. That's the pivot point. All right. So you could think of the pivot point as being the center of that screw thread right there in the center, right at the middle. Whoops, sorry, right at the middle of that screw. All right. So that's like the axis of rotation, infinitely thin if you could draw it. And the same thing here. If I put these two pieces of brass at dissimilar locations like this, it's going to be very difficult for me to keep this from rotating. It's basically going to fall down. Now, wait a minute. What if I hold it like this, straight up and down? It's really easy to keep it from rotating. Huh. Whereas if I try to hold it horizontal, it's very, whoops. I could barely resist it at all. And so clearly there's something weird here. It's not like the forces are changing. The pieces of brass don't change their weights. What's changing here are the distances and the angles. Clearly, distances and angles all have to do with this new concept, torque. Similarly, like this, right? We saw that angles changed if you don't apply enough force here. So there's, in general, we see that torque depends on a couple of things. It obviously depends on the amount of force, but also a distance of some sort and an angle of some sort. These are the factors that affect torque. The mathematical equation for it, torque, that's a Greek letter tau, is R cross F. If I drew a picture of this, at some point, every problem that we're going to discuss, you could consider as having some kind of pivot point. And then maybe this is applied out here. There could be a force applied somewhere that's not at the pivot point. So there's a force out here. All right, and maybe I'll make this stand out. There we go. And the idea is we need to talk about a distance vector. So I'm going to define this one, the displacement from the pivot to the point of interest. You should open up your workbooks to page 69 right now, because page 69 is where all this stuff is defined, and it will help us so you could just listen to me and not have to write as much crap down. So go to page 69 of the workbook, and I'll show you what that looks like. I think this is it. Whoops. Page 69. All right. And so our goal, look at how there's a lot to see on this page. This is the whole page. There's clearly a lot of subtleties in here. And so it's going to take us a while to get through this one. So that's kind of what we want to understand. Now, I think it might make sense to start with this basic definition and kind of do a little example and then show how you could use these equations, and then show you why I'm giving you 4 versions of the same calculation. There's 4 different methods we are possibly going to use to calculate torque. Each one has certain pros and cons, and I would be lying to you if I said that one is good enough for all of them. Many problems, version 3 is the best. Many problems, version 1 is the best. Depending on what your career choice is, certain ones are better than worse. So, yeah. So let's start with this example, just because I don't have to hold it. Okay. And now I want you to think about this, this object right here. And let me actually use this cable to indicate something. You could think here, if I raise this up a little bit. Okay. So what I want to do is I want to imagine this is a long rod like this, and we're just going to kind of exaggerate it a little bit. Okay, and I've got a meter stick here, albeit with some golf balls on it, but that's about 30 centimeters. Just, oh, sorry, 30 centimeters. So that's 70 right there. Okay, so I'm just going to kind of draw this, and this looks like it's about 5 centimeters. So let's say the pivot point right here is 5 centimeters. Let's say that's 30 centimeters. And there's some object clamped onto here. Let's just assume it's a point mass for right now. And let's say the whole rod. Sorry, I can't read here. Let me just do this. I'm just pretending that this is the end of the rod right here. So I'm assuming this whole thing is a rod from right here to right there. It doesn't matter. It's just a demo problem. Let's just say it's about 52 centimeters or something long. Let's just round that to 50. So the whole thing from here to here is 50 centimeters long. And so let's see. So if this is 30 and this is 5, we should be able to figure that out if we need it. All right. So now I just want you to, hopefully this is reasonable to you. I hope you agree that this thing is basically weighing down on the rod. Weighing down, meaning its weight is acting right here, straight down, sort of like this cable is pulled straight down by its weight. So we're going to assume the weight of this thing. I'm just going to assume it's 10 newtons. I don't know. Maybe it's about 1 kilogram. Maybe it's a little less, but whatever. So let's assume that this is exerting some weight force of 10 newtons. Now, the bar itself also has weight that's not negligible compared to 10 newtons. And in fact, this bar probably weighs a little bit more than this device. So I'm going to say the bar itself has a weight of 20 newtons. All right. And now I can get this thing out of the way, and we're trying to analyze all the different forces acting on this thing. All right. And so now in this case, oh, let me see what's in the chat there. Okay. Gotcha. Okay. All right. So in this case, where does the weight of the bar act on the bar? What's your gut tell you?
On the pivot point?
No.
At the end, to the right?
Nope.
Center of mass?
At the center of mass. That's one of the things about the center of mass. Aha. So that would be, oh, geez, if this whole thing is 50, how far over is the center from this pivot point? So again, the pivot point's right here. This distance is 5. How far over do I need to go from the pivot point to get to the location where the weight acts on the rod?
25 or 30?
It's
From the end?
total is 50. So how far do I go from this point?
Oh, would it be 20?
20, yes. Right? So that means right here. Let's say the weight of this, I forget what I said, but let's just assume the weight of that is 20 newtons. Actually, I don't want to do that. Let's say it's 17 newtons, just so we have some weirdo numbers in here, okay? That way I don't have two number 20s to confuse me later. All right. It'll just keep me faster. All right. Oh, whoops. So that means I got to change this down here. Whatever. Let's just say this is 17 newtons. I apologize. Sorry about that. Okay. Sorry. Now, the idea, are there any other forces acting on this bar? Again, we're talking about this thing. Are there any other forces acting on this piece of metal?
Would you consider the pivot point acting against it?
The pivot point does something as well, doesn't it? It's going to have to exert forces some way. Now, I don't know which, though, the size of those, but let's just assume for right now the pivot point's going to exert some force this way and some force this way, and I'm going to call those Rx and Ry. The reason why will be discussed in chapter 12, not now, but it's called the reaction force. Basically, all the other forces, and then the pivot will react to them, essentially, and cause forces maybe this way or that way. At this point, yeah, let's leave it like this. You may say, well, shoot, this thing's not moving. Isn't Rx equal to 0? And I'd be like, yeah, net force, because there's a force pushing this way and that way from the clamp. So the net horizontal force from the clamp is 0. And you end up getting, yeah, whatever. All right. Now, let's try to figure out using, our goal is to learn about torque. The first step when analyzing torque is to draw a new style of FBD. We're not just drawing the forces acting on the object at a dot. We're drawing them exactly where they are placed on the object. Previously, when we did FBDs, we would have just done this, right? And put all the forces at one spot in the center. Now what are we doing? We're drawing not only the forces acting on the object, but we're also correctly placing the tails of each force where they actually apply on the object. That's the first step. Notice that. Okay, so now, so now I can erase this so I have some room to work. Okay, we know all the dimensions in here. Let's see if this is 5 and that's 30. What's this last one? 35. So that should be 15, I think. Figure not to scale. Now we've got all the dimensions if we need them. All right. So in this case, let's first figure out the torque due to the weight of the rod using this formula. I need this R vector for the weight crossed with the weight of the rod. vector. Now, what does R mean? If you have page 69 open, maybe somebody can tell me, what does R mean here? From what to what?
It's the displacement from pivot to point force applied.
Yes. So in this case, what is R vector? Try it. It's okay to be wrong.
Is it 20 centimeters?
No.
Oh.
But that's part of it. What's the difference between this and this?
There's no like direction on it.
Yeah, so
would it
give
be
me the
20
direction.
Centimeters by hat?
Yes, and that is correct. Got it? Subtle difference. Crossed with, well, what is the weight of the rod? Somebody else.
17 newtons negative J hat.
Correct. And I'm just going to write it like that. Are you okay with that? Just put the negative out in front.
Would we still assume, so because we're assuming that the weight's going down, so that's going to be counterclockwise. So if we do the trick with our hand, that'll be negative, right?
I'm going to discuss that at the end. Is that cool?
Yeah.
You're absolutely right, I think. So you're working ahead. Let me get this done first. So, all right. So what do I get when I do this one? It's 20 times 17. So that's what, 340? And notice the units. Now there's a minus sign here. So maybe I'll stick that out front. And what is left? What is that?
Wheel of pain.
Yes. So we go I goes to J goes to K. Now I just would like to point out, I am assuming, just like all of you, when you started telling me stuff, I think you agree that unless we specify otherwise, we're going to assume this is I hat and J hat, right? That's the standard unless we have a good reason to say otherwise, which sometimes we do. But if this is I and this is J, which way does K hat point?
Towards.
Yep.
Straight to yeah.
So notice all that stuff in chapter 3 is finally going to get used. So we have to, if we define I and J this way, we don't get a choice on K hat because we need I to go to J to go to K to go to I to do the wheel of pain. So what's I cross J?
K.
K. And notice I said cross. This is not times, it's cross. So this goes to negative 340 Newton centimeters K hat. That is the torque. Now, let's go to Alonzo's question. What was your question again? About the right hand?
Like if assuming that the rod wants to go downwards where the pivot point is, like the rotating.
So let's take a look at what this means. Maybe what I'll do is I'll group this a little bit prettier just for right now. Do you agree I could just put the negative K hat at the end? That's the magnitude. That's the direction. So watch this. How do we figure out, using the right hand rule, the correct direction for any cross product? Line up the fingers of your right hand with the first vector. Do it, even if you look stupid on your computer there. I need to go, remember, for this problem, that is the vector we're lining up with. From the pivot point to the point where the force is applied. Now notice there's 4 different ways you could line it up. Here's 1, 2, 3, 4. And in fact, there's an infinite number, right? Any of these ways, my fingers. However, just do some trial and error. Like I'm going to go like this first. If I curl my fingers, do they go to the direction of the 17 Newton force? No. How about now? No. How about now? Yes. Notice my thumb points into the page. That means negative k hat. That means the axis of rotation is negative k hat, and this thing would tend to rotate that direction. So the negative k hat means the axis of rotation, not clockwise or counterclockwise, but effectively clockwise or counterclockwise. So in this case, notice if we go this way, that would be clockwise. Negative k hat and clockwise are effectively saying the same thing. Does that make sense? The axis is negative k hat, which means your fingers go clockwise if you line up your right thumb. All right. Now, we could go on and do the next torque. What would be different? Would the direction be different? The torque due to this 10 Newton force.
It should be the same.
Should be the same. Do you think that torque would be larger or smaller?
Larger.
Why do you think it would be larger?
Because it's farther away from the pivot point.
Ah, but what about the force?
Oh, it's smaller.
Yeah, and so it's not obvious, is it? So in this case, we see that 10 times 30 is only 300 Newton centimeters. Yep. Ah, so Gonzalo, you got to get used to it, unfortunately. Or you could do everything left-handed and then just know the answers are backwards. That'll work. Okay. So now, yeah, unfortunately, there are a lot of right-hand rules in physics. There are a lot of physics equations that have cross products in them. Magnetism, for example, mu naught I ds cross b over, yeah, whatever. So yeah, and the Coriolis force, omega cross r. It's a double cross product. You want to get a system. So even if you don't like the right-hand rules, you've got to get good at it some way. And again, like I said, you could always do the left hand and know it's the opposite. I don't recommend that. I'd recommend just try to deal with the right hand, but what do I know? I'm not a lefty. All right. All right. So great. A couple of other things. Units. We talked about the units here. Maybe you've used a torque wrench. Most of you probably have not. But if you look at a torque wrench, usually it's in foot pounds. Okay, or Newton meters. Newton is a unit of force. Now, do you agree we could convert this? I could divide out 100 here. Isn't this 3.4 Newton meters? I hope you see that. So we could actually do Newton meters here. In this case, what's another name for the unit of Newton times a meter?
Joule.
Joule, but nobody uses that for torque. So if you are talking about torques and you write joules, people are going to think you're an idiot. That's just the facts. So you don't write that. So from experience, you're supposed to know if it's an energy problem, Newton times a meter is a joule. And if it's a torque problem, a Newton times a meter is a Newton meter. And that's just the way you talk. And I don't know if that's good or bad, but that's just what society has decided on. Yeah, and here's the other thing. Why don't they call it meter newtons? It makes sense because R is the first thing in the cross product, but they don't. They call it foot pounds, but nobody calls it meter newtons that I've ever seen. So that's just the way life is. Yep. Okay. Gotcha. Yes, so torque, yep. Okay, so torque is a Newton meter, energy is a joule, even though they're the same units. I don't know, whatever. Okay, so let's go look at this page now. That's kind of the ideas. Now, here's the thing. This was a pretty simple one, but it has all the guts. Just think, if this was at some angles and stuff, what would be different? The R vectors would maybe be a little bit harder, and maybe the forces would be a little bit harder, but it's the same general procedure. This procedure I just taught you will work for every single torque problem ever. However, sometimes it's pretty darn slow. So we want to learn clever tricks so that we're always doing these problems as quickly as possible. All right. It's like knowing something versus having to Google it, right? If you know something, it's faster than Google. So you want to know some certain things. These are some tricks to know. So that is the first method we just described. Now, in general, we could do this second method. All right. The second method, I want to point out something strange here. Notice this one is a vector. This is not. But when we see it worked out here, notice I said counterclockwise for this case, or k-hat. It's the same. So these pictures on the right side of page 69 all show the same calculations using method 2, 3, and 4. All right. So we just did a wheel of pain calculation. We'll do another one in a minute. But let's focus on this one here. Sorry, I didn't put the direction right there. In this case, R is the vector from the pivot point to the point where the force is applied. That's R vector. Next, I've got a force vector here, right? So there's the force. That's the applied force. That's that one. We've got the applied force. The angle between, if I want to use this angle, which one should I use? That one or this one, which would be 180 minus theta. Which one is the correct answer? Is it theta or 180 minus theta?
Theta?
Both are correct. This is one of the few cases where you could not know what you're doing in physics and actually get it right. Either one works. It turns out this is a trick. Sine of 180 minus theta equals sine of theta. It's a mathematical luck, stroke of good fortune here. If you don't believe me, consider this picture. There's a trig wheel, right? Let's say this is theta. Well, this is 180 minus theta, right? They both have the same vertical component. They both have the same sign. They have opposite cosines, but they do have the same sign. Whatever. If you don't like that, talk to me later or whatever. Basically, that's a math trick. We could use either angle, good enough. So we're going to do problems like that in a minute, but I just want to point out you could do something similar, and notice this one has an advantage because we don't have to use I hats, J hats, and K hats. If you know distances but not vectors, that's kind of nice. Like, let's say you know this distance, but you don't know all the angles. Let's say you only know one of the angles, this one. Well, this would be a great method to do the problem if you know some distances in one angle, because you know all the pieces to plug in. That's a lot better than writing everything in I hats, J hats. Ugh. That would take some time and would be easy to screw up. All right. We'll do some practice with that in a minute. How do we get the direction? Remind me, how could you get the direction if we don't have the I hats, J hats, and K hats? What would you have to use to get the direction?
Hand method?
Right hand rule. Even though this looks a little bit stupid, I want to show you something here. Whoops, where is it? Here's a trick you could do if you have stuff on paper. And I want you to try this. Get your book out, and what you could do is stick your hand out straight in front of you and rotate the book to match your hand rather than your hand to match the book, right? And so rather than trying to go like, just line up the book with your right hand, curl it. Notice my thumb points out of the page. Sorry, I got to do this so the camera can see it. I line up the paper with my hand here. So I line up the R vector on the paper with my hand, curl my fingers to the F vector, my thumb points out of the page. Okay. So that's method 2. Great method, sometimes very useful, sometimes super fast. And if you only have one torque, sometimes this is the best way to go. We're going to use it a lot. Here's another one that's very, very popular. Now, what does this symbol here mean? R perpendicular. R perpendicular is a thing called a lever arm. Now, what they do in this equation is you basically group the R and the sine theta together. Instead of trying to get just the R vector and the angle separate, you group them in this way right here. First, we need the force. And there's a line of action that runs through that force. Line of action is a critical term to learn. Line of action is a line drawn through the force that extends to infinity in both directions. It's basically this green line, if you could see it, that I just drew here, this dotted line. Remember, there's the force. Give me a second. There's the force. Hopefully that arrow will pop up on your screen in a sec. The line of action is that green line running through the applied force. Now, R perpendicular is this thing right here. It's the distance along a perpendicular bisector, if you want to get spicy with the math terms. It's the distance along the perpendicular bisector that goes from the pivot to that line of action. And that has, if you look, if this side is R and this side is theta, this side ends up being R perp equals R sine theta. Now, we know you're going to get the same answer. All we're doing is we're grouping the R and the sine theta together and calling it this one term R perpendicular. You may be saying, this is really stupid, dude. I don't need this. This is a waste of my, it turns out this will be extremely useful. I promise I will show you how later. It turns out in a great many problems, it's easier to define R perpendicular. So in a lot of problems or real life situations, like hanging a door, it's really easy to give basically measurements of the door, X and Y. Those X and Y will oftentimes relate to the R perpendicular, and it's easier to get the torque this way. All right. Now, questions about that? We are going to do an example in a minute, so you actually could see that. Then, whoops, notice here, F perpendicular, that's just grouping the F and the sine theta together. So I got to scroll down so you can see this. That's this one. And this is a little bit different here. So, sorry, let me make sure you know which one I'm talking about. We're looking at this right here. Notice what I did here. There's a subtlety. What I did is I know in the old days, we would always split up our force components like this. I didn't use the triangle method. Why? It's crucial when we're doing torque because we need from the pivot to the point where the force is applied. So rather than splitting up force components like triangles, I'm going to split them up with their tails located at the original tail. Sort of like in your Python code last week, where the component tails were stuck to the ball, where you said VX arrow and VY arrow and AX arrow, right? You put all the component tails locked to the position. And that's exactly what we are doing here. Now, I want to point something out here. This component will cause no torque. If you think about it, I'm going to call this force parallel. Okay. Now, in this case, R crossed with a force which is parallel to R will equal 0 because the cross product only worries about how perpendicular you are. If you wanted to go this way, you could think of it as R in the R hat, but then that's crossed with a force that's parallel, which is also in the R hat. Well, what's any unit vector crossed with itself?
Is it 1?
It's 0.
0.
Any unit vector dot with itself is 1. Is that helping?
Yeah.
Yeah. If you want to know why, remember this would be 1 times the sine of the angle between. That's what a cross product asks for. What is the angle between any vector and itself? Zero. And sine of 0 degrees equals 0. Does that help, Alonzo, or not?
Yeah.
Yeah, so basically anytime you cross a vector with something that's parallel to it, you end up with 0. Now this stuff seems a little bit weird, but the point being, I just want to point out that this R vector crossed with this part of the force is always going to be 0. If you don't want to remember everything I just said, here's what you could memorize. If the line of action for a force goes through the pivot point, it causes no torque. So this component has a line of action that goes right through the pivot point. And if you just remember this line, you don't have to remember these R hats and parallel hats and all this crap. So just know if the line of action for a force goes through the pivot point, the force causes no torque. All right. And notice here's the component that's perpendicular to the rod. And that gets our calculation right back to the types that we were just doing on the whiteboard a minute ago. All right. So this is a good time to ask any questions you want. Just interrupt at any time. I'm going to bring that screen back up in case you have a question. So any questions about any of this before we do examples?
One question for the stuff to memorize on point 4, the 4th point, is the I. What's the I? What unit's that?
What do you think it is? Let me give you a hint. This equation is similar to, I was actually just going to go through the stuff to memorize, so I guess we'll do this one first. That's Newton's second law in translation land, where everything's just moving left, right, up, down, and not twisting. What is the equivalent? What is I?
Moment of inertia.
Ah, our old friend from last lecture, the moment of inertia. There we go. All right. Good on that, Jess? So I is the moment of inertia. Okay. So now let's look at this. Here is something you really, 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 really want to have down. If the line of action for a force goes to the pivot point, it causes no torque. That's the easiest way to calculate torque. Know that the answer is 0 and be correct. So if a torque is 0, that saves you doing some work. That's a lot better than doing a bunch of math and finding out, oh, I did 6 lines of math and found out something is equal to 0. Not fun. Okay.
Does that
Go ahead.
Does that only apply when you're finding the one of the torque equations for number 4 and the force?
This applies all the time. All the time. So the line of action was defined in the third method, but so this is why that line of action is so useful. If we can use the line of action, if you could draw the line of action for a force or just look at the paper and say, looks like that force has a line of action going through the pivot, I don't bother to work with it for my torque equation. So like we're going to do sum of torques equals I alpha, right? Well, if one of these forces causes no torque, I don't need to waste time figuring it out for that sum. Is that good?
Yeah, I was just getting confused because method 3 and 4 had different lines of action. So they're basically
well, no. This one is I see what you're saying. Yeah, so I was mixing go ahead, Alonzo. Sorry.
It just like depends on how you're seeing or like dividing the.
Let me show you some. So take a look at this problem down here. So this is, I was going to get to this at the end, but might as well talk about it now. This is the line of action for the whole force. However, I could split it into components and do a line of action for one component and a line of action for the other component. So we see, well, everybody but Jesse could see. The green is the line of action. So that's this one. I'll put a G here, and I'll put an R here for red, green, and blue. Okay. So the green line is the line of action for the horizontal component only. The blue line is the line of action for the vertical component only, and the red line is the line of action for the entire force. And look at this. If I try to get the lever arm for the red line, that's this distance. That is the lever arm for the entire force. This is R perpendicular for the entire force. Yeah, I could in theory do it, but yeah. Do you want to figure out this triangle? And do, you see what I'm, whereas, let me get that out of there. It's a lot easier to say, I could get this lever arm really frickin' easy, and I can get this lever arm really frickin' easy. So instead of dealing with one force and one lever arm, it's actually much easier to deal with lever arms on the individual components. I don't know if that goes where you were asking, but does that clarify what I meant?
Yeah.
Yeah. So you could do a line of action for the entire force or a line of action for each component. And it sounds like you got that. We'll come back to that in a minute. That's in an example problem too. So we'll do some numbers with this to make sure you got it in a minute. Okay. All right. So memorize that. This is a trig identity. If you just look at a triangle, let's say this is theta. Let's say this side is 1. This angle would be 90 minus theta if it's a right triangle. Notice this side down here is cosine of theta, but it's also sine of what?
90 minus theta.
And that's where the relationship comes from. You're going to see this a lot for the rest of the semester. So you need to memorize this one. It's just going to save you time. The idea is so many times we have thetas and we have 90 minus thetas. You just want to know that if you have sine of 90 minus, you could switch it to cosine, and vice versa. Cosine of 90 minus theta equals sine theta. And then this was a trig identity I just told you about that it's just useful to know. This one is useful to know because it tells us I could use this angle right here. Sorry, give it a second for Zoom to show it up. I could use this angle, or I could use the big angle over here on the other side, 180 minus theta. Either angle works for figuring out torque. Next, why are we caring about this? Because it's the equivalent of Newton's second law in rotation land. Sum of torques equals moment of inertia times angular acceleration. Watch out, torque's a vector. Watch out, remember that direction. And in standard math notation, just being clear, we usually have I hat this way. We usually have K hat this way. J hat this way. And we have K hat would be into or out of the page.
Out of the page?
Out of the page. So again, if you line up the thumb of your right hand with K hat, your fingers are curling counterclockwise. If you line up the fingers of your left hand opposite K hat, they're going clockwise. So that's why we say clockwise and counterclockwise relate to K hat this way. Watch out, physicists are schmucks, right? We'll sometimes say, hey, you know what? Sometimes you'll see me draw it and I'll just say this way is positive. Right? And so sometimes I'm going to deliberately flip things because if everything's rotating clockwise, I'm going to call it clockwise positive. I'm that kind of guy. I'm a very positive guy. Sure. All right. And don't forget that. We talked about the right-hand rule. We talked about this occasionally useful style. That is really all of that page. So now we've done that whole page. Let's do a problem. Let's look at 10.36. Okay, I'm going to start writing this up on the whiteboard. You can do whatever you want. Because you don't really understand things without doing a problem once in a while. It's a complicated thing. You got to learn concepts. You got to be able to code it, and you got to be able to actually compute it by paper to check your codes. Gee, I wonder why physics is so hard. I'm just drawing it up. I'll share my whiteboard in a minute. Still writing. Okay, got it all here. Sorry that took so long. Next, we are in part A. We're not trying to get the torque in part A. It just says, get the R vector for me, will you? Somebody, what do you think? It's okay to be wrong. Just speak up and you'll learn more. Take a stab at it.
Is it 1.50 meters?
Okay, that's the magnitude of the R vector. But let me rephrase. I want you to get it to me in I hat, J hat form, Cartesian form. So it's 1.5 this way. How would you get the X component only?
Would it be 1.50 sine of theta?
Nope.
I hat.
No. You're almost there. It's killing me. What's that?
Plus cosine 1.5
meters.
30.
Units. So Dead is doing the other part.
Yeah, sorry.
And maybe you said it, but I didn't hear it. So my apologies. Just when we start plugging in numbers, then we got to be, picky about units and all that crap. So I'm just keeping you. Yeah. Now, wait a minute. Is this plus or minus? Okay. So in this case, oh, wait, what did I screw up? What did I forget?
The J hat.
Nice. Nice job, Mark. And whoever else just spoke up too. Thank you. All right, good. Okay, so that is the R vector. You could punch this crap in your calculator and we got it. Good enough. All right. What is part B? Getting the torque probably. Whoops, wrong page. Yeah, part B is get torque. Well, torque is always equal to R cross F. I know what F is in Cartesian form. I know what R is. To save some time and get this done, let's look at the workbook together now. Okay. Let's look at the solution. There it is. All right. And maybe I'll make this a little bit bigger here. Okay. So, do you see this? What did I screw up right there?
Use sine twice.
Yeah, that should be a cosine. All right. And then over here, here's the first one. Here's the second one. Notice I was just being picky about the units because we know we want to end up with Newton times meters. In this case, I got an I cross I. Any term with an I cross I is equal to 0 because any unit vector crossed with itself is 0. Dotted with itself is 1. Well, yeah, unit vectors. So that we can get rid of those terms. So when you write them all out, we only write out the terms we need to keep. So I write out the I cross J and the J cross I. Notice I get an I cross J term, but a J cross I term. From the wheel of pain, the I cross J is K hat. The J cross I is negative K hat. And we get this big old mess, which gives us this torque. How could I check that answer? What is one way to check it? Maybe this will help. How could I check the direction?
The wheel of pain trick?
You could do the, I was going to say right-hand rule, but that's the equivalent to the wheel of pain trick. So line up the fingers of your right hand with that R vector, and then curl your fingers to F, and you should see your finger points into the page, which according to the coordinate system we were given in the problem, that is correct, negative K hat. Again, if I line up my fingers this way, curl the right hand fingers to this, my thumb points into the page, that corresponds to negative K hat. It's so easy to screw up these cross products by a minus sign. It's worth doing that check. That's all I wanted to say. Units check, direction is correct. Odds of us getting this right are decent. Questions about that?
So we put the negative for the K hat out front.
Yeah, well, you could do it either way. You could say, let me rephrase. Both of these are equally good ways to say it. They have 6.9 Newton meters, negative K hat. Now, to be honest, most people are lazy, and writing the minus sign out front means you don't have to write the parentheses, so most people go that way. But this is the magnitude, this is the direction. There's a reason to write it in that longer way, so that's also okay with me. Cool? If you were coding it, this way might make more sense to you, where you write magnitude times a vector. And so that, yeah, this might be a way you see it in a code. Is that cool?
Oh, good. Yeah. Thank you.
Okay, got it. Now, let's go back to this one. I know you know how to do this. We just did it. But I'm saying let's do, and some of your books might not have this depending what version you have. But now we're going to do the same thing by determining lever arms for each component. Now, just to save us some time, let's look at it and see if you understand it. So we've got Fy, which is in red here. And we've got Fx, which is in blue here. Notice I drew lines of action for each of those. And then what did I do? This right here is the perpendicular distance to the blue line of action, to the F sub x line of action. So again, we've split this thing into components. And got the line of action for F sub x only, and got the lever arm for that. Notice the lever arm, or R perp. You're going to hear me say this a lot. What is R perp? As in perpendicular perp? All right. So what's R perp? Well, that is 1.3 from doing SOHCAHTOA, piece of cake. It's really easy to get torque 1. Torque 2, that's also fairly easy. I get R perp for the Y component. right? This is the LOA, the line of action for Fy. And I can see, okay, that's pretty straightforward. So I can get this torque and that torque. And then I could do a quick right-hand rule to get the directions. Do a quick right-hand rule to get the direction. And it's actually pretty quick to get the two torques separately. So I can get this one and I could get that one. Now, is this the fewest number of calculations possible? Absolutely not. That was the previous method. However, just like we've seen in computer science, in the coding labs, sometimes it's wise to split things into smaller parts, which are easy to understand, and then add them together line by line. So that's kind of just a technique you could use. To be honest, I would not use this method for this problem. I would have used the first method. But any questions on this method to see if you needed to use it? Does that help? I'm leaving this up here just a little bit longer than usual, just because that's a lot of information. So let me bring the zoom up so I can see you. What do we think? Is this pretty good, people? Okay. Okay. You could always watch the live stream or read the solution or whatever. All right. So there's that. We now, I would say you now understand how to calculate torques in a couple of ways. Obviously, you need a lot of practice. So that's what that's what's coming next. Let's take a look at one of these here. Let's go back to here. Take a second and look at 10.37. And I'm going to lower this down just so I can hopefully see all of them. There we go. All right, so there I've got all of those cases. So 10.37, we've got our coordinate system shown right in the middle, standard X, Y, Z. If you don't see that drawn, that's what we're assuming all the time. Notice we have to be very good with our three-dimensional coordinate systems. The first thing you always do is check, does X go to Y, go to Z? Or does I hat go to J hat, go to K hat? Does. All right, let's just find the direction of torque. Take a second and try this, okay? That way you can find out if you have any questions. Remember, what does X mean on this one?
Into the page?
Into, good. And what does the dot mean on case 4?
Out the page.
Out. Okay, so take a second. You've got the answers yourselves, but just stick the papers, put the book there, and just move your right hand and just a couple really quick, okay? I'll put the clock on so I know. I'll give you a minute and a half. Almost there, 5 seconds. Sorry, I'm trying to get another demo set up. I'll give you a couple more seconds just because I'm trying to get this screw threaded. Sorry. Come on. There we go. Good enough. All right. So any questions about those cases? If we look at the solutions really quick, there's the answers. Whoops. Get that junk off of there. So notice case 5 and case 6 were 0. Trick questions there. So let's go back and look at those and see what is a good way to describe why case 5 or case 6 has no torque. Give me the reasoning.
Line of action is on the pivot point.
That's it. Line of action is through the pivot point. Yeah. On the pivot point, through the pivot point. That's either one is good. Excellent. So, and notice that same reasoning works for both case 5 and case 6. Some of you might have said the force acts at the pivot point for case 5. That is excellent reasoning. However, I want you to get used to this verbiage. Line of action runs through the pivot. It's just more general because that also tells us why case 6 is no good. Now, at the risk, I don't know how well this is going to turn out because I'm on a headset mic here, but I just want to show you some kind of basic concepts of torque applied to opening a door. So obviously you guys know how to open a door, right? But we have, I want you to think about the torque equation here as I'm doing this, and hopefully the mic can pick up what I'm saying. And I'm going to be, it'll seem silly, but maybe this makes sense. Now, before I go over there, where's the axis of rotation for the door?
The hinges.
The hinges. So remember that. Okay. So let me see if this doesn't pick up. Oh, well, we tried. Okay. So hopefully you can hear me. This is a bad way to open or close a door. Right? If I push this way, it's terrible. Why?
It's the same direction as the hinges.
So when we do that, it's not a good way to open the door. You need to have a force component that's perpendicular in the direction you want to rotate it. So it's not that we're not applying a force there, but that force doesn't cause any torque about that axis. Right? All right. So then we could also try it one other stupid way. If I try to shut the door right here, you can do it, but it's pretty hard to get it all the way shut. You're not going to shut a door like that. It's because it's not that it's impossible. You're applying a force perpendicular in the direction that you need to. However, your lever arm is so small, you need a huge force to close it. So it's a dumb idea to close a door by pushing on it close to the hinge. It's not that it can't be done. It's that the force becomes ridiculously large, or the force required becomes ridiculously large. So you kind of know this stuff already. The direction you push and the location at which you push can change things. Let's do this example right here.
I have a question.
Yes, I'm listening.
I know the door won't close if you pull it up, but you're like pulling it parallel to the axis. How would that work?
Well, so in this case, it's tricky. I was kind of glossing over something because in that case, right, if you look at it right here, there's the axis of rotation, right? The hinge. And so in that case, this door is constrained to move only about that axis. So if you want to apply a force that causes it to rotate, that force has to be perpendicular to the plane of the door. Otherwise, the door can't rotate about that axis. Now, if this was not a hinge, but was instead like a ball joint where you could swivel it in any way, then maybe you could push on it in some weird way and cause it to swivel. But for doors, they've got 2 hinges, which restricts us to only that axis of rotation, not infinitely many. Is that kind of...
Yeah, so there could be a problem where the axis of rotation is constrained, and we have to see if it will work or not.
Generally speaking, I'm going to keep it simple in this class. I'm going to say, look, here's a pivot point, and then it's always going to rock around that pivot in the direction you expect. Is that good for right now?
Yeah.
It's kind of vague and lame, but yeah. So if you're not sure like which way the pivots rotate, you want to look at the book. And so I did technically use an engineering design for most of these pivots. Let me show you. So when you see a pivot in a engineering class, actually, it looks like this first one I drew. Whoops. Oh, sorry. When you see a pivot like this, that has a technical meaning like this in an engineering physics class. This symbol means it's free to rotate this way and no other way. So it's constrained to rotate about this pivot point in that plane. Got it?
Yes.
And there's different types of physics, different types of pivots. So this is called a roller. And so a roller can actually roll left and right. If you put a bridge up, you don't want it to collapse when the weather gets hot. And so sometimes you'll put one end of a bridge on a roller, or sometimes there's even a rocker where it's this pivot and there's a pin that looks like this, kind of like a hammerhead, and the entire bridge can rest on this. That way, when it gets hot or cold, as the bridge expands and contracts, one end can rock back and forth and the bridge doesn't collapse. Or sometimes you've seen these expansion joints where you'll see part of a roadway that looks like this. Now, this is getting way off topic, but the idea is they'll have these nested teeth like this. That way you could drive over it even if there's a small gap. But as it gets hot or cold, you can have this. That way you don't have the railway buckle. Or maybe you've seen pictures of oil pipes that look like this, where they run and there's like a horseshoe shape in it. And the idea is when it gets hot or cold, these can expand and contract. There's a lot that goes into this that we don't have time to cover right now that will be covered in other physics and engineering courses. I should stop. Alonzo, you're good on your question?
Yes.
All right. Okay, so there's a lot that goes into this, and it gets cooler once other factors get involved. We're not going to deal with that now. Yeah. Let me do another one here. Even after I spent all that time getting this thing on here, now I'm going to have to take it off. I forgot about something I wanted to show you. Okay. Look at this right here. Screw, right? So now what's happening when I put a screwdriver into here? The axis of rotation is right down the middle of the screw, right? Now, when you do this, what are you actually doing? Well, the tip and each tip of the screwdriver is applying a small torque and causing the screw to rotate, right? So when you do this, each end, the left and the right end, actually are exerting forces. One's pushing this way, one's pushing this way, depending which way I'm rotating. And the ends of that screwdriver are causing the torque. So you could imagine, what about a Phillips head or a star bolt? Well, then you could have more than 2 points of contact. Maybe there's a good or a bad issue with that. Now, there's pros and cons to Phillips and flatheads and all these things, whatever. But it's the same principle for tightening a screw or for mounting things onto here. All of these things are basically the same. Torque. All right, and let me see where we're at here. I'm going to leave 10.38 for you to do at home. And this is a good one for checking right-hand rules. It's basically, I kind of did everything for you today, so you can kind of see, do you actually understand what we've already done by doing this one at home later? And we're going to pick up here. I want to take a short break. Okay, so let's take a short break. So just a couple of minutes, and then we'll take another break right before the quiz. Okay, so we're going to take just 2 to 3 minutes. 3 minutes tops, and then we'll get back into it. So just get some water, go to the bathroom, and come right back. And I promise I'll give you another break at about 10 minutes before the quiz. Okay. Okay. Take a short break. All right. All right. So we need to start the quiz at 6:15. So I'll try to give you a break. Certainly no later than 6:10. But yeah. All right. Hopefully at about 6:05 if we get through everything. So, all right, let's take a look here. Let's put it all together and do a practical problem. So let's look at 10.39. I'm going to take a minute to draw it up on the board. You can do what you need to do. I'll share my whiteboard in a minute. All right. So actually, let me do, before I start, what are we trying to figure out here? What is angular acceleration? What symbol is that?
Alpha.
Alpha, fish swimming left. All right. Is that a scalar or a vector?
Vector.
Vector. All right. So notice it doesn't say determine the magnitude of it. It says determine angular acceleration. That said, okay, cool. Now, we probably need a coordinate system. I'm assuming we should use the standard coordinate system, right? Unless we have a good reason to otherwise. Now, for torques, a lot of times what I'll do is I'll draw this way, and I'll just say this is a positive torque. That way it's clear. It's a different version of the coordinate system. It's just saying, hey, look, any torques that would cause a rotation, in this case, what is that? Counterclockwise, I'm considering positive. So there is a coordinate system if we need it. All right. And we know the mass, the length, the force, and I'm going to assume we know this angle because it's given in the figure. All right. Okay, so here we go. We know the mass of the rod. We know the length. We know theta, and we know F. That's our givens. Sorry if that's a bit small and sloppy. What should we do? What's something I might write down? Help me.
Your R vector.
R vector. Okay, for this force right here.
Yes.
Okay, what is that R vector?
Would it be Rx would be going from the pivot to the right, and then from the pivot to the up, or up, going up?
Oh, you mean, oh, so you're saying the reaction force vector. You're saying this. Rx and Ry, that?
Yeah.
Yes. So those are the forces acting at the pivot. Yes, absolutely. Are there any other forces acting on this object?
Would we say the center of mass of the rod going down?
Yeah. What's a good name for that force?
Center of mass? Force?
I would say just mg, right?
Yeah.
Yeah. So, okay, the force acts at the center of mass with magnitude mg. Okay. How does this help me get angular acceleration? Right? We're supposed to find fish swimming left. How does this stuff help?
Could you use the sum of torque equals inertia times alpha?
Absolutely. So, which forces cause no torque?
The R ones.
Yes. Why?
They're on the line of actions on going through the
Yeah, good.
pivot.
You got it. Line of action through the pivot for these two. So we don't need to worry about them for this. So we could have gotten by without even drawing them. And in a lot of classes, in a lot of textbooks, they won't draw these in chapter 10. They will draw them in chapter 12. So I'm trying to foreshadow chapter 12. Anytime you have a pivot point, it's possible it could push to the right or to the left. Look at this one. Do you think this pivot point is pushing to the right or to the left, given that we're pulling that way on the rod? If I pull on this rod, let me get you the visual for this. That's what I was trying to set up here. And now I'm just going to get super lazy. All right. I'm going to use this piece of brass to symbolize the center of mass right about there. Sorry. I don't know. It's close enough to the middle. So pretend we know the weight is going to act in the middle. I'm trying to hold this thing and keep it from twisting. And then I'm going to pull on it this way. So the force is on this hand, right? This is supposed to be a simulation of that. This is the mass at the center. My finger right here that I'm showing you is the pivot point. So Rx and Ry or whatever, right? It has to hold it up. And then this hand is the other force pulling it this way. If my fingers over here are pulling it that way, oh gosh, whatever. Rx is going to turn out to be a negative number. Can you see that? I don't know how to say this online. I don't know. It's killing me. All right. Anyways, so good enough. We don't need this. We don't need this. So what's the torque due to force F? And the torque due to mg. That's our two forces that we need to worry about. Those are going to add up to, whoops, moment of inertia times angular acceleration. What's one? How do I get the force? How do you want to do the torque due to F? Which method? 1, 2, 3, or 4?
1.
Okay. I'm going to let you do that. I want to pick a different way. Because 1 is doable, but it's, I don't know. Okay, I guess we could do it 1.
Your way, please.
What 1 is works, Jacob, but it's also the slowest here.
Maybe 3 or 2.
We split it up in components.
2,
And then-
3, or 4 are all faster than 1 for this one.
I see. Yeah, I see.
So it's not that you're wrong, right? You could have said the R vector is equal to L in the I hat, but then you'd have to say, oh, shoot, the force vector is, you could see I'm already slowing down. So you could do that. Okay, so in fact, what I would choose to do is I would just say, isn't it L times the force times the sine of the angle between in the K hat? That's what I would do. I'm going to show you that in slow-mo. It's R, for this one, it's the distance L, times the force magnitude, times sine of the angle between. What's the angle between them? This is the R vector, right? For that upper one. So that's the R vector for force F. What is the angle between them?
Sine theta?
No.
90 minus theta.
90 minus theta is the angle between. Or you could say 90 plus theta, but I don't have a trig identity for that. So this is the angle between that line and that line. It's the angle between the line of action and the line from the pivot point to the, okay. So this would be a 90 minus theta. Aha, what's sine of 90 minus theta?
Cosine theta.
Cosine theta. Iota theta. Tasty. Okay, next. And K hat. K hat. Line up the fingers of your right hand with the R vector for force F. Curl them to force F. Thumb points out of the page. That's a K hat in this case, assuming standard coordinate system. Whew. Got it? What's the torque due to mg? Somebody else do that one. Somebody try it. Somebody other than me. Use this same technique. Method 2. What's the distance for mg?
L over 2.
L over 2. What's the force magnitude for mg?
0.
mg. Just mg, right? And then what is the, so it's 0 if you had a massless rod, but this rod we were told has mass. Okay. And then what's the angle between?
0.
No.
Oh,
This is the R vector for mg.
90?
90. What's sine of 90?
1.
1.
1. What direction?
negative K hat.
Yep. And all that has to equal I alpha. Oh man, this is getting cramped. All right, let's rewrite. So this is now L, F, cos theta, K hat. I'm going to bring the minus sign out front. minus L over 2 mg k hat. What's the moment of inertia? Yeah, you got to look it up, right?
Would it be 1/3 ml squared?
Winner, winner, chicken dinner. Oh, geez, I'm losing it. 13 hours of Zoom a day and no fun makes Jack a dull boy. All right. I'm kind of starting to cross my references and talk to myself in this weird parallel Zoom universe. Anyways, all right. Do you agree you could solve for alpha at this point? You got everything in there. You solve for it. What is a logical thing that we do almost every time we see problems like this? We ignore the k-hat, ignore the vector, even though we know it's a vector. If the answer turns out positive, we know it's positive k-hat. If the answer turns out negative, we know it's negative k-hat. Sort of like in chapter 2. So we see this all the time, and it was really painful in chapter 2, but now that you're kind of used to it, I hope that's not so weird. So if I look at the solution, I didn't even write the k-hats in the solution. You know what I'm saying? I said there's an implied k-hat on all terms. And so that's what it looks like. Are there other ways to do this? You bet. We could have done exactly what Jacob had asked. It only would have taken one extra line, but I'm so broken as a human being right now. One extra line of math would have killed me right now. So, all right. Any questions about that? This is, look at my R vector. Notice how it goes to the left. That's what I was trying to say. Dude, isn't this going to pull to the left? If this force pulls to the right, this one probably pulls to the left is what I was trying to say earlier, and I failed. More on that in chapter 12. So in chapter 12, we basically focus on how to get the reaction force given everything else going on in the problem. Whew. All right. Question 10.40, 10.41, and 10.42 are all pretty good problems for you to do later. They're simple. All the forces are at right angles, but notice you're supposed to get alpha and A. And I think these are good for you. Think about a hockey puck or something, right? With some forces applied to it. If you could look at these three problems, 10.40, 10.41, and 10.42, the arrows represent forces that are applied. Which one of these things is going to have alpha equals 0?
The one on the bottom.
Why do you say the one on the bottom? This one, right?
Well, yeah, because that's two forces, like parallel and towards the center of mass.
So will this force cancel that force?
Yeah.
It will in terms of translation, but not rotation. Think about it. If you push this way and somebody else pushes that way on a merry-go-round, they push together. This one has the largest angular acceleration. Do you see that or not? Let me show you with a piece of foam. Watch this. Whoops. Oh. Hold on. Look at this. I'm going to put my hand on the bottom and on the top. If I push the same way, it translates. If I push opposite ways, it rotates. So this is called a force couple, something you engineers will learn about in dynamics class. But in the idea here is if one person applies a force this way and the other applies a force that way, it's kind of hard for me to do this. How about like this? It's going to rotate and it's not going to go anywhere. Do you see that? Now that I'm actually centered, it's not translating when I do that. So force couples cause a rotation, but no translation. They cause it to spin with an omega, but they don't give it a translational velocity V. Let's go back into there. So that was a good guess. Gonzalo, did that address your question?
Yeah.
So this one is going to have a huge alpha.
Okay. So in that case, it has to be the middle one.
Yes. So notice this one would cause a rotation, but it cancels that rotation. This one, why does this one cause no rotation?
Pointing towards the center of mass.
Where do things rotate in general if there's no pivot point shown? About their center of mass. So if you apply some forces to a satellite, that satellite's going to spin about its center of mass. Now, if you bolt a pivot point on it, like so, notice this is a lot to take in, right? If you don't show a pivot point, you assume the pivot point is an object's center of mass, unless there's some reason to understand otherwise. More on that next time. But yeah, so like if you spin something, it's going to rotate about its center of mass if you throw it across the room. If you don't believe me, take a wrench, throw it at your wall, and watch it spin, and then pay for the damage to your own wall. Okay. Or don't, and just believe me. That's the other choice. Things spin about their center of mass. If you want to see this, take a piece of foam and throw it outside. But who's got the time for that? All right. Normally when we're in class, I literally start throwing pieces of foam across the room, and you could see which dots spin and which don't, but I don't have that right now. All right. We're getting close to break time, right? So let me show you this one, 10.43. Here I'm talking about torque, but I'm showing you a plot of omega versus t. How do those things relate? How does torque relate to a plot of omega versus t? What can you get from a plot of omega versus t? There are two things that jump out at me. Other than just omega values, what else can you get? If it helps, think of the rotational equivalent. What can you get from a VT plot?
Angular acceleration.
Yeah, we could get, how do you get angular acceleration from this plot?
Omega over t.
Slope. Yes.
So, yeah.
So you could get alpha from the slope, and then you could say, oh, well, I know sum of torque equals I alpha. They all have the same moment of inertia. So wherever this thing has the largest slope, it's going to have the largest torque. This is going to be a large torque. There's no torque, no torque, no torque, small torque. Okay. And things like that. So that's cool. Toilet paper. Worry about that later, but if you want, we'll talk about this. We don't have that. And then I'm going to show you a couple of quick videos here. So 10.46, am I on the right one? Yeah. You know what? Let me just show you in the solutions and make sure these video links work. Because you could watch these on your own later. I just want to make sure the links work in case I need to update them. Okay, that's that. Let me see if this link works. That's working. And let me check the next one. I think you're good to go for a break. Whoops. Looks like they're both working. So and I'll give you your break here, but I just want to point out this problem, 10.46 and 10.47 are common demos, and I made videos of those demos so you can watch those demos. I haven't done every demo, but there's two of them. So when you're working on 10.46 and 47, you can actually see that. It's more important that we take a break now so that you're rested here. So I see the time is 6:09 on my clock. You know what? Since I got this video here, I'm going to show it just for fun. If you want to not watch this video, that's cool. I understand. So I'll go back one just so I could show you this one. I think it's neat. Why is there an ad? I thought I told these things to have no ads. I don't know. All right. So here, I'm going to slow it down even slower. And I'm going to start this thing from the beginning. There's a bunch of pennies on a meter stick. Watch it. See how some of the pennies come off the meter stick? These pennies are not touching the meter stick, but these pennies all are. It's because this pivot point is exerting a force upwards, which slows the fall of this end of the rod, but this end of the rod ends up speeding up and falls at a rate faster than G. And the cutoff is at 2/3 of the length every time when you do this. So if you are wanting to understand why these pennies come off the ruler and these pennies stay on the ruler, that's what that problem is about. And why does this magic number of 2/3 L show up? You can do the math, plug in the moment of inertia, 1/3, and that will help you understand this. And notice the mg over 2 is where the lever, so the 2 and the 3 come from that. Now that said, let's just show the other one, which is cool. Whoops, what did I do? Come on. This is a fun one. Notice the ball is initially below the level of the cup. The ball starts below the cup, but the cup falls faster than G and the ball falls into it. A student did all these cool effects, not me. You could see the cup falls faster than the ball, which is in free fall. And the ball just barely misses. Isn't that cool? That's all. If you want to understand that one, that's the next one. I swear I got to stop so you can get a break in. All right, stop. Sorry about that. Take a quick break, use the bathroom, come back. We're going to do random breakout rooms. And this is your last group activity, and you'll get that done. The group quiz starts, and I'll make the breakout rooms now. You can come back whenever and get the thing and start up. Okay. So you could take your break, and when you come back, Canvas has got the quiz waiting for you. Yes. Whatever time Canvas starts is when it does, because my clock I know isn't exactly the same as everybody's and stuff.
Do you want us to join the breakout rooms now, or just wait till?
You can do whatever you want. I don't care anymore. I gave up on everything now. Just trying to get to this damn. It's intense. Good job today, everybody. Sorry, somebody joined, and now I got to remake them because they didn't have the right number of people in them. Sorry, my bad. It's always something.